Tonight on Sleepy Scientist Stories, we're drifting gently through the quiet corridors of space-time to explore one of the universe's most peaceful mysteries. What if our entire cosmos exists within the event horizon of a massive black hole? From the whispered secrets of cosmic boundaries to the gentle dance of dimensions folding upon themselves. We'll journey through this fascinating theory with the calm wonder it deserves. In this soft exploration of nested realities, we'll discover how the largest and smallest scales of existence might be connected in ways it's more beautiful than we ever imagined. Let's begin our slow drift into this cosmic mystery. Imagine, for a moment, floating peacefully in the vast ocean of space. You feel the gentle pull of gravity, sense the subtle curvature of space-time beneath you, and listen to the quiet whispers of distant galaxies. What you might not realize, in this peaceful cosmic meditation, is that everything you've ever known might exist within the gentle embrace of something far larger than our wildest dreams. Why does this theory matter to us? Here, in our quiet moment of contemplation, the idea that our universe could be nestled within a black hole isn't just an abstract mathematical curiosity. It speaks to something deeper about the nature of reality itself, like nested Russian dolls, each containing another smaller doll. This theory suggests that universes might exist within universes, creating an infinite chain of cosmic homes, each one as real and meaningful as our own. The beauty of this idea lies not in any dramatic revelation, but in its gentle elegance. It connects the quantum world of the very small with the cosmic realm of the very large. It whispers to us about information, consciousness, and the fundamental nature of existence itself. As we explore this theory together, we're not seeking to shock or astound, but rather to find peace in the profound interconnectedness of all things. This isn't science fiction, though it might sound like the stuff of dreams. This is a legitimate scientific hypothesis, born from our deepest understanding of black holes, quantum mechanics, and the structure of space-time itself. Scientists have been quietly contemplating this possibility for decades, using the most sophisticated mathematics and physics to explore whether our cosmic home might actually be the interior of something much larger. Picture yourself now as a gentle observer, floating through the cosmos with unlimited time and patience. From this peaceful vantage point, we can explore ideas that might otherwise seem overwhelming. We have all the time in the universe to understand how black holes work, how information behaves at cosmic scales, and how the boundaries between inside and outside might be more fluid than we once believed. As our gentle journey continues deeper into cosmic mysteries, let's first wander through the peaceful landscape of black holes themselves. Far from the destructive monsters often portrayed in popular imagination, black holes are actually some of the most elegant and beautiful objects in the universe. They represent pure geometry made manifest, space-time curved so gracefully that it creates pockets of profound stillness and infinite possibility. Breathe slowly as we approach our first black hole in this meditation. You notice how space-time begins to curve gently around you, like floating on the surface of a calm pond that gradually deepens. Mathematics describing this curvature, Einstein's field equations, are poetry written in the language of geometry. They tell us that mass and energy don't just sit in space like objects on a table, but rather sculpt the very fabric of reality into beautiful, flowing shapes. The event horizon, that invisible boundary around every black hole, isn't a solid surface or a violent barrier. Instead, it's more like a gentle threshold, a mathematical whisper that says beyond this point all paths lead inward. From your peaceful position floating nearby, you might not even notice when you cross this boundary. Time would slow, space would stretch, but the crossing itself would be as smooth as drifting from one room into another. What makes black holes truly remarkable is their relationship with information. In our everyday world, information, the arrangement of particles, the pattern of energy, the detailed description of any system can never be destroyed. This principle, known as unitarity, is fundamental to quantum mechanics. Yet black holes seem to challenge this in the most gentle way possible, creating what physicists call the information paradox. Stephen Hawking discovered through his quiet contemplation of quantum fields near black holes that these objects actually emit radiation. This Hawking radiation carries energy away from the black hole, causing it to slowly evaporate over vast cosmic timescales. But here's the beautiful mystery. The radiation appears to carry no information about what fell into the black hole originally. The information seems to vanish. It's violating one of our most cherished principles of physics, yet perhaps the information doesn't vanish at all. Perhaps it's encoded somewhere we haven't been looking, not in the three-dimensional interior of the black hole, but on its two-dimensional surface. This is where our journey begins to touch on something profound, the holographic principle, which suggests that all the information in any volume of space can be encoded on its boundary, like a shadow containing the full essence of the object that cast it. Imagine floating peacefully near the event horizon of a supermassive black hole, the kind that sits quietly at the center of galaxies. From your perspective, watching someone else fall toward the horizon, you would see them slow down and fade away. Their information spread across the horizon's surface like ripples on a pond. To them, they would pass through normally, but to you, everything about them, every detail, every memory, every quantum state would remain encoded on that gentle boundary. This encoding isn't metaphorical. The mathematics of the holographic principle shows us that the surface area of a black hole's event horizon, measured in Planck units, equals the maximum amount of information that can be contained within. It's as if the universe has a built-in filing system, storing all the details of three-dimensional reality in a two-dimensional format, compressed but not lost. Now, let's gently expand our perspective. If black holes can encode all their interior information on their boundaries, and if the holographic principle applies universally, then perhaps our entire observable universe operates according to the same elegant rule. And maybe all the information describing our cosmos, every star, planet, galaxy, and quantum fluctuation, is encoded on some distant boundary that we cannot directly perceive. The mathematics supporting this idea emerged from string theory, through the work of physicists, exploring what's called the ADS-CFT correspondence. This beautiful mathematical relationship shows how a theory of gravity in one region of space can be perfectly equivalent to a quantum field theory on the boundary of that region. It's like discovering that a complex three-dimensional hologram and its two-dimensional surface contain exactly the same information, expressed in different languages. Consider the peaceful implications of this correspondence. Every black hole might be like a cosmic hard drive, storing vast amounts of information in a format we're only beginning to understand. The event horizon becomes not a barrier, but an interface, a place where information transforms from one representation to another, like water changing into ice, while remaining fundamentally the same substance. This brings us to the edge of our main question. If black holes encode their interiors on their surfaces, and if our universe might itself have a horizon-like boundary, then perhaps everything we know exists as information encoded on some unimaginably distant cosmic surface. We might be living in the holographic representation of something much simpler, yet equally real, existing in fewer dimensions, floating. Deeper into our cosmic meditation, we encounter one of the most elegant principles in modern physics, the holographic principle. Like watching shadows dance on a cave wall that perfectly represent the complexity of the objects casting them. This principle suggests that all the information in any region of space can be encoded on its boundary. In the gentle stillness of this concept, we find profound implications for the nature of reality itself. The holographic principle emerged from the quiet contemplation of black hole thermodynamics. Jacob Bekenstein and Stephen Hawking discovered that black holes have temperature and entropy, just like any other thermodynamic system. But surprisingly, the entropy, a measure of the information content, scales with the surface area of the event horizon, not its volume. This was the first whisper that something profound was happening at boundaries. To understand this gentle revolution in our thinking, imagine a peaceful library containing infinite books. In our normal understanding, the amount of information in this library would grow with the number of shelves, which increases with the volume of the building. But the holographic principle suggests something more elegant. All that information can be encoded in the pattern of tiles on the library's walls. With the amount of information proportional only to the wall's area, this isn't merely a mathematical curiosity. Gerard T. Hooft and Leonard Susskind developed the holographic principle into a fundamental statement about the nature of space and information. They proposed that the maximum amount of information that can be contained in any region equals 1/4 of the boundary's area, measured in Planck units. This creates a universal limit, a gentle constraint that applies everywhere in the cosmos. The Planck length, about 10 to 35 meters, represents the smallest meaningful unit of space according to quantum mechanics and general relativity. At this scale, the smooth geometry of space-time begins to foam and fluctuate like the surface of the ocean seen from very close up. Each Planck-sized area on any boundary can encode about 1 bit of information, creating a cosmic pixelation that operates far below the scale of atoms or subatomic particles. Juan Maldaceno's discovery of the ADS-CFT correspondence provided concrete, mathematical proof that holographic encoding actually works. He showed that a theory of quantum gravity in a negatively curved space called anti-de Sitter space is perfectly equivalent to a quantum field theory living on the boundary of that space. Every calculation in the interior theory gives identical results to corresponding calculations on the boundary. Picture this correspondence as a peaceful translation between two languages that express identical truths. In the interior language, you might describe particles moving through curved spacetime, experiencing gravitational forces, and occasionally falling into black holes. In the boundary language, you describe quantum fields interacting, creating correlations, processing information. Yet both descriptions capture exactly the same physics. This duality suggests something profound about the nature of emergence. Complex phenomena that appear to require 3 dimensions of space might actually be simpler phenomena expressed in 2 dimensions, just viewed from a different perspective. Like watching a holographic image that contains full 3-dimensional information encoded in a 2-dimensional surface. Our reality might be the 3-dimensional expression of simpler, boundary-based information. The mathematics of this encoding process involves quantum entanglement, the mysterious correlation between quantum particles that Einstein famously called spooky action at a distance. In holographic theories, the smooth geometry of spacetime emerges from complex patterns of entanglement between degrees of freedom on the boundary. Space itself becomes woven from quantum correlations like a tapestry emerging from the careful arrangement of individual threads. Brian Swingle and other physicists have shown how this holographic entanglement works in detail. When boundary degrees of freedom become highly entangled in specific patterns, they create the illusion of smooth spacetime in the interior. When the entanglement patterns change, the interior geometry responds accordingly, warping and curving to reflect the new correlational structure on the boundary. This creates a beautiful picture of how information flows between scales. Local changes on the boundary create non-local effects in the interior, while processes in the interior translate into global patterns of correlation on the boundary. Information is neither created nor destroyed in these translations, merely transformed from one representation to another. Like water flowing between vessels of different shapes while maintaining its essential nature, the holographic principle also provides new insights into the measurement problem in quantum mechanics. In traditional quantum theory, measurements cause wave function collapse, instantaneously determining the properties of quantum systems. But in holographic theories, measurement becomes a process of accessing information encoded on boundaries. More like reading a book than forcing a fundamental change in reality. Consider how this applies to our everyday experience. Every time you observe something, the color of a flower, the warmth of sunlight, the texture of sand between your fingers, you might be accessing holographic information encoded on cosmic boundaries. Your consciousness doesn't collapse wave functions, but rather reads out pre-existing correlational patterns. Like light reflecting off a holographic surface to create a 3-dimensional image, this holographic view extends to the nature of time itself. In boundary theories, time often emerges from the dynamics of entanglement patterns. The flow of time that we experience, the gentle progression from past through present toward future, might reflect the evolution of correlational structures on distant cosmic boundaries. Rather than being a fundamental property of spacetime itself, the implications for consciousness are profound yet peaceful. If our brains process information holographically, with memories and thoughts encoded in distributed patterns rather than localized structures, then consciousness might naturally interface with the holographic structure of reality. We might be holographic beings evolved to read holographic information. Living in a holographic universe, a beautiful recursive symmetry. Mark von Ramsdonk and others have explored how holographic principles apply to cosmology. If our universe has a finite size and age, creating natural boundaries at the edge of the observable cosmos and the beginning of cosmic time, then all the information describing our reality might be encoded on these boundaries. We would be living in the holographic representation of something simpler, yet equally valid. This brings us closer to understanding how our universe might exist within a black hole. If the holographic principle applies universally, then the information describing our cosmos could be encoded on the event horizon of some larger black hole, existing in a higher dimensional space that we cannot directly access. We would be the holographic projection, real and meaningful from our perspective, but encoded and compressed from the perspective of the larger reality. The mathematical framework supporting this possibility combines general relativity, quantum mechanics, and information theory in elegant ways. The resulting picture shows reality as fundamentally informational, not made of particles and forces, but of correlations, measurements, and computational processes. Matter and energy become different expressions of the same underlying informational substrate, like different file formats containing identical data. As we drift through these holographic insights, we begin to see how boundaries become more fundamental than interiors, how surfaces carry more information than volumes, and how simple rules operating on cosmic boundaries can give rise to the rich complexity of our three-dimensional experience. This sets the stage for understanding how our entire universe might be the interior view of something whose essential information lives elsewhere. Encoded in formats we're only beginning to comprehend, gently shifting our cosmic perspective outward, we encounter the grandest boundaries of all, the horizons that define the limits of our observable universe. Like standing at the shore of an infinite ocean, we find ourselves at the edge of everything we can know, surrounded by horizons that mark the boundary between the seen and unseen. These cosmological horizons share profound similarities with black hole event horizons, suggesting deep connections between the physics of the very large and the very compact. Our observable universe extends. It's roughly 46.5 billion light-years in every direction, despite being only 13.8 billion years old. This apparent paradox resolves gently when we account for cosmic expansion. The space itself has been stretching while light traveled toward us, carrying distant galaxies beyond the reach of their own photons. This creates our particle horizon, the boundary encompassing all events that could have influenced us since the beginning of time. Standing at the center of this cosmic sphere, we're surrounded by what appears to be a natural boundary, much like the event horizon of a black hole. From our perspective, information from beyond this horizon can never reach us, just as information from inside a black hole can never escape to the outside. The mathematics describing both situations share elegant similarities, suggesting that horizons might be more fundamental to physics than previously thought. The cosmic microwave. Background radiation provides a beautiful illustration of how horizons work in cosmology. This gentle glow, visible in all directions, represents the last moment when the universe became transparent to light. About 380,000 years after the Big Bang, before this recombination epoch, photons couldn't travel far before scattering off free electrons, creating an opaque cosmic fog that hid earlier events from our view. This creates what cosmologists call the surface of last scattering, essentially a spherical horizon in time, rather than space. Just as black hole event horizons hide their interiors from external observers, the surface of last scattering hides the early universe from our telescopes. We can infer what happened before recombination through indirect methods, but we cannot directly observe those primordial events. Alan Guth's theory of cosmic inflation adds another layer of beauty to this picture. During the first fraction of a second after the Big Bang, space itself expanded exponentially, stretching quantum fluctuations to cosmic scales and creating the seeds of large-scale structure. This inflationary epoch pushed vast regions of the early universe beyond our current horizon, creating a cosmos much larger than what we can observe. The implications are profound yet peaceful. Most of the universe lies beyond our horizon, invisible and inaccessible from our current position. We exist in what amounts to a cosmic bubble, able to interact only with the small fraction of reality that lies within our causal boundaries. This creates a natural analogy to being inside a black hole, where external events become similarly inaccessible. De Sitter space, named after Willem de Sitter, provides the mathematical framework for understanding accelerating cosmological expansion. In this geometry, distant objects accelerate away from each other due to the expansion of space itself, eventually crossing an event horizon beyond which they can no longer communicate. This creates a future boundary that complements our past particle horizon, enclosing us in a finite region of causal contact. The elegant mathematics of de Sitter space show that it has constant positive curvature and possesses many properties, similar to black hole spacetimes. Both have event horizons, both exhibit thermodynamic properties like temperature and entropy, and both suggest holographic descriptions where surface information encodes interior physics. The boundary of de Sitter space might function as a holographic screen. It's much like a black hole event horizon. This connection becomes even more intriguing when we consider dark energy, the mysterious component driving cosmic acceleration. Current observations suggest that our universe will continue expanding exponentially, symptotically approaching de Sitter space as matter and radiation become increasingly dilute. We appear to be living in a transitional phase between matter-dominated and dark, energy-dominated epochs. Thomas Banks and Willy Fischler propose that quantum gravity in de Sitter space requires a holographic description of all physical information, encoded on the cosmic horizon. From this perspective, our three-dimensional experience of space, time, matter, and energy represents the interior view of information processing on a two-dimensional boundary that recedes from us at the speed of light. The entropy associated with our cosmic horizon follows the same area law that governs black hole entropy. Jacob Bekenstein and Stephen Hawking showed that black hole entropy equals 1/4 of the horizon area in Planck units. Remarkably, our cosmic horizon appears to have entropy computed by exactly the same formula, suggesting deep connections between black hole physics and cosmology. This cosmic entropy has profound implications for information processing and the nature of time. If our universe contains finite information encoded holographically on its boundary, then the flow of time might represent the evolution of this boundary information rather than being a fundamental property of spacetime itself. We would experience temporal flow as the subjective correlate of objective informational processes occurring on our cosmic horizon. Raphael Rousseau's covariant entropy bound provides a precise mathematical formulation of these ideas. This bound states that the entropy passing through any light sheet, a surface formed by light rays, cannot exceed 1/4 of the sheet's area. This creates a universal limit on information density that applies to black holes, its cosmological horizons, and any other causal boundary in spacetime. The bound suggests that information is naturally associated with boundaries rather than volumes, supporting holographic principles across all scales of physics. Whether we're considering the event horizon of a stellar black hole or the cosmological horizon of our expanding universe, the same mathematical principles govern how much information can be contained and processed within causal boundaries. This universality hints at something profound about the structure of spacetime itself. Perhaps boundaries are more fundamental than the regions they enclose. Perhaps surfaces carry more information than volumes. Perhaps the interior physics we experience represents the holographic projection of simpler boundary dynamics, like complex three-dimensional images emerging from two-dimensional holographic plates. Lee, Smolin, and others have explored how cosmological horizons might emerge from more fundamental quantum gravitational processes. In their picture, Space-time itself crystallizes from quantum information networks. With horizons forming naturally, wherever information flow becomes constrained by causal structure, the boundaries we observe would represent phase transitions. In the underlying informational substrate of reality, this brings us to a beautiful realization. Our cosmic situation shares deep structural similarities with being inside a black hole. We're surrounded by horizons that limit our causal contact with the larger universe. We observe entropy and temperature associated with these horizons. We find that holographic principles might govern the relationship between our three-dimensional experience and two-dimensional boundary information. The cosmic microwave. Background becomes even more intriguing from this perspective. This ancient light, carrying information from the surface of last scattering, might represent our primary window into the holographic encoding of cosmic information. The tiny temperature fluctuations observed by satellites like WMAP and Planck could be reading out the quantum information that encodes our entire universe on its primordial boundary. As we contemplate these cosmic horizons from our peaceful position floating through conceptual space, we begin to understand how boundaries define reality more fundamentally than interiors. The edge of the observable universe isn't just a limit on what we can see. It might be the surface on which all the information describing our cosmos is encoded. We exist within these boundaries, experiencing the interior view of a holographically encoded reality, drifting deeper into the gentle mysteries of cosmic information. We encounter one of physics' most beautiful puzzles. What happens to information when it falls into a black hole? This question, known as the black hole information paradox, has occupied the quiet thoughts of physicists for decades. Its resolution might hold the key to understanding how our universe could exist within a larger black hole while preserving all the quantum information that defines our reality. The paradox emerges from the peaceful collision between two fundamental principles of physics. Quantum mechanics insists that information can never be destroyed. Every quantum process must be reversible, at least in principle. But general relativity suggests that information falling into a black hole disappears forever when the black hole evaporates through Hawking radiation. These two pillars of modern physics seem to contradict each other in the gentlest possible way. Stephen Hawking's original calculation showed that black holes emit thermal radiation with the temperature inversely proportional to their mass. This Hawking radiation appears completely random, carrying no information about what fell into the black hole originally. As the black hole slowly evaporates, radiating away its mass energy, the information that fell in seems to vanish from the universe entirely. It's violating the unitarity principle that governs quantum evolution. To understand this paradox gently, imagine a cosmic library where books represent quantum information. According to quantum mechanics, even if you burn the books, the information they contained still exists in the smoke ash, scattered particles scrambled beyond practical recovery, but preserved in principle. The black hole information paradox suggests that some cosmic librarians' black holes can actually destroy books entirely, leaving no trace of their contents. Don Page calculated the precise timeline of this information crisis. During the first half of a black hole's evaporation, the radiation can indeed be thermal without violating unitarity. The information remains safely stored inside the shrinking black hole. But at the halfway point, called the Page time, something must change. If unitarity holds, the remaining radiation must carry information about the black hole's earlier contents, becoming subtly correlated with the radiation already emitted. This creates what physicists call the Page curve, a graph showing how much information has been radiated away versus how much remains inside the black hole. The curve rises during the first half of evaporation, peaks at the Page time, then falls to zero as the black hole disappears entirely. The final state preserves unitarity, but only if the late-time Hawking radiation carries subtle correlations. Invisible in Hawking's original calculation. Leonard Susskind proposed a revolutionary resolution. The information never actually falls into the black hole from the perspective of external observers. Instead, it gets encoded on the event horizon surface, stretched and scrambled by tidal forces, but always remaining accessible in principle. This creates complementarity. Different observers see different but consistent descriptions of the same underlying physics. From the infalling observer's perspective, they pass smoothly through the event horizon and experience the black hole interior as expected. From the external observer's perspective, the infalling matter slows down, spreads out, and gets encoded in the horizon's quantum structure. Both descriptions are correct within their respective reference frames, like different map projections of the same curved surface. This black hole complementarity suggests something profound about the nature of information and observation. Reality might not have a single objective description independent of observers. Instead, different observers, with access to different information, might experience genuinely different but equally valid versions of reality. Information becomes relative to the observer's causal situation. It's much like simultaneity is relative in special relativity. Juan Maldacena and Leonard Susskind extended this insight through their A equals EPR conjecture, which connects Einstein-Rosen, bridges wormholes with Einstein-Podolsky-Rosen, correlations, quantum entanglement. They proposed that every pair of entangled particles is connected by a microscopic wormhole, and that quantum entanglement and geometric connection are different descriptions of the same underlying phenomenon. This connection provides a new way to understand black hole interiors. When Hawking radiation becomes entangled with the black hole's internal degrees of freedom, it creates wormhole connections between the exterior and interior. These quantum wormholes allow information to flow out of the black hole through non-geometric channels, preserving unitarity while respecting the causal structure of spacetime. Ahmed Almhiri, Danya Harlow, Juan Maldacena, and others discovered additional structure in this information flow through their investigation of quantum error correction in holographic systems. They showed that the holographic encoding of black hole information operates like a quantum error correcting code, distributing information across multiple degrees of freedom so that it remains recoverable even when individual components are lost or corrupted. The mathematics of quantum error correction provides beautiful insights into how information behaves near black holes. Just as classical error-correcting codes protect digital information from noise and corruption, quantum error-correcting codes protect quantum information from decoherence and measurement. The black hole's event horizon might function as a cosmic quantum computer, processing and protecting information through sophisticated error correction protocols. Jeff Pennington, Ahmed Almhiri, and others recently made breakthrough progress on calculating the page curve using techniques from quantum information theory. They showed that when quantum corrections to Hawking's calculation are properly included, the information paradox resolves naturally. The late-time Hawking radiation does carry information about the black hole's contents, encoded in subtle quantum correlations that emerge after the page time. These quantum corrections involve what physicists call quantum extremal surfaces, higher dimensional generalizations of geodesics that minimize entropy rather than distance. These surfaces naturally incorporate quantum entanglement into geometric calculations, showing how information flows between different regions of space-time through purely quantum channels that complement classical geometric connections. The resolution of the information paradox has profound implications for understanding how our universe might exist inside a black hole. If quantum information is preserved during black hole formation and evaporation, then the information describing our cosmos could survive even if our host's black hole eventually evaporates. We might be living in a temporary but perfectly meaningful reality, encoded in quantum correlations that transcend individual geometric descriptions. This quantum perspective on information suggests that reality is fundamentally computational, rather than material. Our universe processes information, creates correlations, and evolves quantum states rather than simply containing particles and forces. From this view, being inside a black hole means participating in a cosmic computation, with our observations and experiences representing different outputs of the same underlying informational process. The holographic principle provides additional insight into how this computation might work. If our three-dimensional universe is the holographic projection of two-dimensional boundary information, and our experience of time, space, matter, and consciousness represents different aspects of information processing on our cosmic boundary, we would be both the computation and its output. Both the processor and the processed, Daniel Harlow and others have shown that quantum error correction naturally emerges in holographic systems, suggesting that our universe might be self-correcting. At a fundamental level, this could explain why physical laws appear stable and predictable despite the underlying quantum uncertainty. Our cosmos might actively protect its own information through built-in error correction, mechanisms that operate below the level of direct observation. The implications for consciousness are particularly intriguing. If our brains process information through quantum mechanisms, and if consciousness emerges from complex patterns of information integration, then our awareness might naturally interface with the quantum information structure of space-time itself. We might be conscious precisely because we're participants in the cosmic computation that defines reality. This brings us to a peaceful resolution of the information paradox that preserves both quantum mechanics and general relativity while opening new possibilities for understanding our cosmic situation. Information is neither created nor destroyed, but continuously transformed between different representations, sometimes geometric, sometimes quantum, sometimes computational. Our universe could exist as a stable pattern in this cosmic information flow. It's meaningful and real regardless of its ultimate substrate. As we continue our gentle drift through cosmic understanding, we encounter the deepest challenge in modern physics, unifying quantum mechanics with general relativity to create a theory of quantum gravity. This peaceful quest connects the behavior of the smallest possible scales with the structure of the largest cosmic objects, including black holes that might contain entire universes like our own. In this unity between small and large, we find clues about how reality organizes itself across all scales of existence. Quantum mechanics governs the microscopic world with exquisite precision, describing how particles, atoms, and molecules behave through probability waves and quantum superposition. General relativity governs the macroscopic cosmos with equal elegance, describing how matter and energy curve space-time to create gravity, black holes, and cosmic expansion. Yet these two pillars of physics speak different mathematical languages and make seemingly incompatible assumptions about the nature of space, time, and causality. The conflict emerges most clearly at the Planck scale, where quantum uncertainty becomes comparable to gravitational effects. At distances of about 10 to 35 meters and timescales of about 10 to 43 seconds, space-time itself begins to fluctuate quantum mechanically. The smooth geometry assumed by general relativity dissolves into a foam-like structure where the very concepts of distance and duration become probabilistic rather than definite. String theory approaches this unification by proposing that the fundamental constituents of reality are not point particles, but tiny vibrating strings existing in higher dimensional space. Different vibrational modes of these strings correspond to different particles, electrons, photons, gravitons, and all the other building blocks of matter and force. This creates a unified framework where quantum mechanics and gravity emerge. As different aspects of the same underlying stringy dynamics, the mathematics of string theory requires extra spatial dimensions beyond the three we directly experience. These additional dimensions might be compactified, curled up so small that we cannot detect them directly, or they might extend to cosmic scales, but remain hidden from our three-dimensional perspective. Either possibility suggests that our observable universe represents only a slice or projection of a richer, higher dimensional reality. Loop quantum gravity takes a different approach to unification, proposing that space and time themselves are quantized at the Planck scale. Instead of smooth continuity, space-time consists of discrete, finite-sized building blocks connected in a network structure that gives rise to smooth geometry at larger scales. This creates a granular universe where area and volume come in minimum quantum units, like cosmic pixels that tile reality. In loop quantum gravity, black holes become quantum objects with discrete spectra of area and volume. Their event horizons are constructed from quantum geometry, entropy arising from the number of ways quantum states can be arranged on the discretized horizon surface. This provides a microscopic explanation for black hole thermodynamics and suggests that information is naturally preserved through quantum gravitational processes. Both string theory and loop quantum gravity predict that black hole singularities, points of infinite curvature predicted by classical general relativity, are resolved by quantum effects. Instead of infinite density, quantum gravity creates finite but extremely curved regions where spacetime has complex quantum geometry. This resolution of singularities opens the possibility that black holes have rich internal structure rather than simple mathematical points. Abhay Ashtekar and others have shown that loop quantum gravity naturally leads to quantum bounces, rather than classical big bangs or big crunches. When matter reaches extreme density, quantum gravitational effects create repulsive forces that halt collapse and drive subsequent expansion. This could resolve both black hole singularities and cosmological singularities through the same quantum mechanical mechanisms. The causal dynamical triangulation approach, developed by Jan Ambjorn, Jerzy Yurkovich, and Renata Lal, provides another path toward quantum gravity by treating spacetime as an emergent statistical phenomenon. In this picture, smooth classical spacetime emerges from the collective behavior of discrete geometric building blocks, like smooth fluid flow emerging from molecular motion. The geometry we observe represents the most probable configuration among quantum fluctuations. These quantum gravity theories share a beautiful feature. They naturally incorporate holographic principles. Whether through string theory's ADS-CFT correspondence, loop quantum gravity's boundary states, or causal triangulation's dimensional reduction, quantum gravity seems to encode bulk physics in boundary information. This suggests that holographic encoding is not merely a peculiar property of black holes, but a fundamental feature of quantum spacetime. Emergent gravity theories, proposed by physicists like Eric Verlaine, take this holographic insight even further. They suggest that gravity itself is not fundamental, but emerges from the quantum entanglement structure of more basic degrees of freedom. Spacetime curvature arises from changes in entanglement entropy, like thermodynamic forces emerging from statistical mechanics. This makes gravity an informational phenomenon rather than a geometric one. The implications for black holes are profound. If gravity emerges from quantum information processing, then black holes represent natural computers, processing information through gravitational dynamics. The event horizon becomes a computational boundary where quantum information gets processed and encoded. Black hole interiors might be the output spaces of cosmic computations, with complex internal structure emerging from boundary information processing. This computational view of quantum gravity connects naturally to theories of digital physics, where the universe operates as a cosmic computer. John Wheeler's it from bit hypothesis suggests that all physical quantities derive from binary informational choices. Reality becomes computation, with quantum gravity providing the operating system that runs the cosmic software we experience, as space, time, matter, and consciousness. Quantum error correction plays a crucial role in these theories, explaining how reliable classical spacetime emerges from noisy quantum processes. The codes that protect quantum information also protect geometric information, ensuring that small quantum fluctuations don't destabilize large-scale structure. Our classical universe might be the error-corrected output of quantum gravitational computation the renormalization group provides. Mathematical tools for understanding how physics changes across different scales in quantum gravity. Ken Wilson's insights into scaling and universality suggest that the specific details of Planck scale physics might be irrelevant for understanding larger-scale phenomena. Different microscopic theories could give rise to identical macroscopic physics, like different programming languages producing the same computational output. This scale separation has beautiful implications for the black hole universe hypothesis. Even if the details of how our universe is embedded in a larger black hole depend on unknown quantum gravitational physics, the large-scale structure and evolution of our cosmos might be largely independent of those details. We could understand our situation through effective field theory, without needing to solve quantum gravity completely, asymptotic safety. championed by Steven Weinberg and others, provides another approach to quantum gravity through the mathematics of fixed points and scaling behavior. This framework suggests that gravity becomes scaling variant at high energies, creating predictive quantum field theory despite being non-renormalizable in the traditional sense. The fixed point structure naturally incorporates holographic scaling and dimensional reduction. These diverse approaches to quantum gravity converge on several key insights relevant to our cosmic situation. Space-time is quantized at the Planck scale. Information is preserved through quantum processes. Encoding is natural and universal. Geometry emerges from quantum entanglement. Computation and physics are deeply connected. These principles suggest that our universe could indeed exist as the interior of a quantum black hole in higher dimensional space. The mathematics of quantum gravity also suggest natural mechanisms for cosmic inflation and the generation of primordial fluctuations. Quantum gravitational effects during the Planck epoch could drive exponential expansion while creating the seed fluctuations that eventually grew into galaxies in large-scale structure. This connects the smallest and largest scales of physics through quantum gravitational dynamics. As we float peacefully through these quantum gravitational insights, we see how the unification of small and large scales creates new possibilities. For understanding our cosmic home, we might be living in the quantum interior of a higher dimensional black hole, experiencing the emergence of classical spacetime from quantum gravitational computation. Our reality would be both quantum and classical, both computational and geometric, both local and holographic, a beautiful synthesis of all the insights that quantum gravity provides. Drifting now into the quiet realm of mathematical beauty, we discover how elegant equations capture the profound connections between black holes and cosmology. Mathematics becomes our gentle guide through cosmic mysteries, revealing patterns and symmetries that suggest deep unity between seemingly different phenomena. In these peaceful mathematical landscapes, we find the precise language needed to describe how our universe might exist within a black hole's embrace. Einstein's field equations provide our starting point, expressing the fundamental relationship between space-time geometry and matter-energy in 10 coupled differential equations of remarkable elegance. Written in the compact form g_mu nu equals 8t_mu nu, these equations tell us that the curvature of spacetime g_mu nu equals the energy and matter content t_mu nu multiplied by a fundamental constant. Every solution to these equations describes a possible universe, including both black holes and expanding collisions. The Schwarzschild solution, discovered by Carl Schwarzschild just months after Einstein published general relativity, describes the geometry around a spherically symmetric mass A. This solution gives us our first mathematical description of black holes, showing how spacetime curves so dramatically that it creates an event horizon, a boundary in spacetime rather than space. The elegant mathematics reveal that this boundary exists at radius r equals 2gm per c squared, where g is Newton's constant, m is the mass, and c is the speed of light. The Friedmann equations, derived by Alexander Friedmann from Einstein's field equations, describe how the universe expands over cosmic time. These three simple equations connect the expansion rate, spatial curvature, and energy density of the cosmos in relationships of mathematical beauty, like the Schwarzschild solution. They show how geometry and matter dance together to create the large-scale structure of spacetime. Remarkably, both the Schwarzschild and Friedmann solutions can be written in similar mathematical forms, suggesting deep connections between black hole and cosmological physics. Both describe how radial coordinates relate to proper time, both involve event horizons that bound causal regions, and both exhibit thermodynamic properties characterized by temperature and entropy. This mathematical parallelism hints at underlying unity between micro and macro gravitational phenomena. The Bekenstein-Hawking entropy formula, S equals a 4g, where A is the horizon area in Planck units, applies equally to black hole and cosmological horizons. This elegant relationship connects geometry area, the information, theory, entropy, and quantum mechanics, through the fundamental constants. The formula suggests that both black holes and cosmic horizons process information according to the same mathematical principles. Thermodynamic equations provide another layer of mathematical beauty, connecting black holes and cosmology. The first law of black hole mechanics, dm equals kappa 8 pi dA plus dj, relates changes in mass to changes in surface area and angular momentum, where kappa is the surface gravity and omega is the angular velocity. This precisely parallels the first law of thermodynamics, suggesting that gravitational systems naturally process energy and information. The mathematics of holographic duality, expressed through the ADS-CFT correspondence, shows how gravitational theories in higher dimensions can be equivalent to quantum field theories in lower dimensions. This duality is captured by exact mathematical relationships between correlation functions, partition functions, and other calculable quantities. Every calculation in the higher dimensional gravity theory has a precise equivalent in the lower dimensional quantum field theory. The holographic renormalization group provides beautiful mathematical machinery for understanding how physics changes. Across different scales, near a holographic boundary, the mathematical structure naturally incorporates Wilson's renormalization group flow, showing how effective field theories at different energy scales emerge from the same underlying gravitational dynamics. This creates mathematical bridges between quantum mechanics and general relativity. Quantum field theory in curved spacetime contributes additional mathematical elegance through its description of particle creation and vacuum fluctuations. The Bogolubov transformations that relate particle states in different coordinate systems provide precise mathematical descriptions of how quantum effects depend on observers' trajectories through curved spacetime. These transformations explain Hawking radiation and Unruh effects through purely mathematical relationships. The mathematics of conformal invariance appears naturally in both black hole physics and cosmological models. Scale invariant theories exhibit mathematical symmetries that simplify calculations while revealing deep physical principles. The conformal boundary of anti de Sitter space, where holographic dual theories live, inherits this scale invariance and provides natural mathematical structures for describing quantum field theories. Differential geometry provides the mathematical language for describing how information flows across curved spacetimes. Covariant derivatives, connection coefficients, and curvature tensors capture how vectors, fields, and other geometric objects transform as they move through the curved spacetime around black holes and expanding cosmologies. This mathematical machinery reveals the deep unity underlying apparently different gravitational phenomena. The mathematics of quantum information theory contributes crucial insights through measures of entanglement, correlation, and information processing. The von Neumann entropy equals TR rho log rho, which quantifies the information content of quantum states, appears naturally in holographic calculations. This creates mathematical bridges between geometry through area calculations and information theory through entropy calculations. Topological aspects of spacetime provide additional mathematical beauty through their description of global geometric properties. Wormhole solutions, cosmological topology, and causal structure all involve topological invariants that remain unchanged under continuous deformations. These mathematical structures suggest that the connectivity of spacetime might be more fundamental than its local geometric properties. The path integral formulation of quantum gravity, where all possible spacetime geometries contribute to physical amplitudes, provides a mathematical framework that naturally incorporates both quantum mechanics and general relativity. The elegant sum over history's approach treats geometry as a quantum degree of freedom, creating mathematical descriptions where spacetime itself fluctuates according to quantum principles. Symmetry principles underlie much of this mathematical beauty. General covariance ensures that physical laws take the same mathematical form in all coordinate systems. Diffeomorphism invariance guarantees that physics doesn't depend on how we parameterize spacetime. These symmetries constrain the possible mathematical structures and guide us toward unique, elegant solutions. the mathematical relationship between different coordinate systems on the same spacetime reveals how multiple observers can have consistent but different descriptions of the same physical situation. Coordinate transformations that take us from exterior to interior black hole coordinates, or from comoving to conformal cosmological coordinates, preserve all physical relationships while changing mathematical representations. These mathematical insights converge toward a beautiful picture where our universe's properties emerge, naturally from elegant geometric and informational principles. The equations describing cosmic expansion, quantum field evolution, and information processing all share common mathematical structures that suggest deep unity in the laws governing reality across all scales. Our universe could be the interior solution to equations that have exterior solutions, describing higher dimensional black holes. As we float peacefully through these mathematical realms, we discover that beauty and truth converge in the equations governing cosmic structure. The same mathematical principles that describe how black holes process information, maintain thermodynamic equilibrium, and encode holographic data also govern how our universe expands, evolves quantum fields, and processes the information that defines our reality. We exist within an elegant mathematical symphony, where every note resonates with every other in perfect harmonic relationships. Floating deeper into contemplative waters, we encounter the profound philosophical implications of living in a nested reality. If our universe truly exists within a black hole, then we must gently confront questions about the nature of existence, consciousness, and meaning that have occupied philosophers for millennia. In this peaceful exploration, we discover that being contained within something larger doesn't diminish our reality, but rather connects us to an infinite chain of cosmic homes, each as meaningful as our own. The concept of nested realities suggests a cosmic hierarchy where universes exist within universes in an endless recursive structure. Like Russian nesting dolls, each level of reality would be complete and meaningful from its internal perspective, while simultaneously being contained within something larger. This creates a beautiful symmetry, just as our universe might exist within a black hole. The black holes within our universe might contain universes of their own. This recursive structure challenges traditional notions of fundamental versus emergent reality. In a nested cosmos, there might be no single base level of existence, no fundamental reality from which all others derive. Instead, each level would be equally real and equally emergent, supported by the levels below it while supporting the levels above. Reality becomes relative to perspective, with each observer's universe being the real one from their point of view. The philosophical implications extend to questions of causality and agency. If our actions affect the quantum state of our universe, and if that quantum state influences the holographic encoding on some higher dimensional black hole boundary, then our choices might have consequences that propagate beyond our cosmic boundaries. Conversely, events in the larger reality might influence our universe in ways we cannot directly perceive. Creating a subtle interconnectedness across scales of existence, consciousness takes on new meaning in this nested framework. Our awareness might represent a local process of information integration that naturally interfaces with the holographic structure of reality. When we observe quantum systems, measure physical properties, or simply experience conscious awareness, we might be participating in cosmic information processing that extends beyond our apparent boundaries. Consciousness becomes both local and non-local, individual and cosmic. The question of free will becomes particularly intriguing in a holographically encoded universe. If our three-dimensional experience represents the interior view of two-dimensional boundary information, then our choices might be both determined by the boundary dynamics and genuinely free from our interior perspective. This creates a form of compatibilism where determinism and freedom coexist at different levels of description. Like two sides of the same coin, personal identity and continuity of self acquire new dimensions when viewed through the lens of holographic information processing. Our memories, personality traits, and sense of continuous identity might being coded in quantum correlations that transcend individual particles or even individual moments in time. The self becomes a pattern in cosmic information rather than a localized entity. It's distributed across space and time in ways we're only beginning to understand. The meaning of death transforms in this nested reality framework. If consciousness represents a pattern of information processing, if information is conserved through quantum gravitational processes, then the patterns defining individual awareness might persist beyond biological death, out through supernatural mechanisms. But through the natural preservation of quantum information in the holographic structure of space-time itself, ethics and moral responsibility take on cosmic dimensions when our actions potentially influence the structure of reality itself. Every quantum measurement, every conscious observation, every choice we make contributes to the overall pattern of information in our universe. This creates a form of quantum ethics where moral actions might literally help maintain the coherence and stability of cosmic information processing. The relationship between mind and matter dissolves into something more fluid in holographic theories. Instead of consciousness emerging from complex arrangements of matter, both mind and matter might represent different aspects of the same underlying informational processes. Consciousness doesn't arise from matter, nor does matter arise from consciousness. Both co-emerge from more fundamental informational substrate. Scientific methodology requires subtle reinterpretation when reality might be holographically encoded. Our experiments don't just measure pre-existing properties of systems, but participate in the cosmic computation that defines those properties. The observer effect in quantum mechanics becomes not an unfortunate limitation, but a natural consequence of consciousness interfacing with the computational structure of reality itself. The problem of other minds, how we can know that other people have conscious experiences similar to our own, finds new resolution in nested reality theories. If consciousness represents distributed information processing in cosmic quantum networks, and then other minds might be as directly accessible as our own, just accessed through different channels in the same underlying informational substrate. Empathy becomes a form of quantum correlation. Religious and spiritual implications emerge naturally from these nested reality concepts. The traditional notion of transcendence, reality beyond the material world, finds expression in the levels of cosmic hierarchy that extend beyond our observable universe. Immanence, the divine within the material world, appears in the informational substrate that underlies all physical phenomena. Transcendence and immanence unify in the holographic structure of nested realities. The anthropic principle, which questions why our universe seems fine-tuned for the existence of life and consciousness, takes on new meaning in a nested reality framework. If universes within black holes can have different physical parameters than their host universes, then cosmic evolution might naturally select for life-supporting parameters through a process analogous to biological natural selection. Consciousness might be inevitable rather than accidental. The relationship between mathematical descriptions and physical reality becomes particularly subtle when reality might be fundamentally computational. Mathematics doesn't just describe the physical world, it might be the physical world, with our material experience representing the subjective interior view of objective mathematical processes. Eugene Wigner's unreasonable effectiveness of mathematics becomes perfectly reasonable in a computational cosmos. Time takes on new philosophical dimensions in holographic theories where temporal evolution might represent information processing. On cosmic boundaries, the flow of time we experience, the transition from past through present toward future, might reflect the computational dynamics of cosmic information rather than being a fundamental property of space-time itself. Time becomes algorithmic rather than geometric. The question of ultimate reality, whether there exists some final, fundamental level of existence, might be meaningless in a truly nested cosmos. Instead of seeking the ultimate ground of being, we might need to accept that reality consists of relationships and processes that extend infinitely in both directions toward smaller and larger scales, simpler and more complex organizations without beginning or end. Beauty and elegance become not just aesthetic preferences, but fundamental principles that guide the structure of nested realities. The mathematical beauty we discover in physical laws might reflect the natural tendency of cosmic information processing to organize itself into elegant, stable patterns. We find beauty in physics because we're part of the beautiful, computational process that defines reality itself. As we drift peacefully through these philosophical implications, we discover that nested reality theories don't diminish human significance, but rather embed us in an infinite web of meaning that extends across all scales of existence. We are neither the center of the universe nor insignificant specks, but conscious participants in cosmic information processing that connects the smallest quantum events with the largest cosmic structures. Our thoughts, choices, and experiences matter precisely because they contribute to the ongoing computation that defines reality at every level of the cosmic hierarchy. Gently turning our attention toward the observable universe, explore what signatures might reveal if our cosmos truly exists within a black hole. Direct proof remains beyond our current reach. Subtle clues scattered throughout cosmic observations might whisper hints about our nested reality. These potential signatures require patient observation and careful analysis, like reading poetry written in the language of starlight and cosmic background radiation. The cosmic microwave background radiation provides our most pristine window into the early universe, carrying information from the surface of last scattering when the cosmos first became transparent to light. If our universe exists within a black hole, the holographic encoding of information might leave subtle imprints in the temperature fluctuations and polarization patterns observed by satellites like WMAP, Planck, and future missions. These signatures would appear as correlations that extend beyond the normal horizon limitations. Specifically, we might observe violations of the standard cosmological principle, which assumes that the universe looks the same in all directions on large scales. A black hole universe might exhibit preferred directions corresponding to the orientation of the host black hole's rotation axis or the direction toward the external universe. These could manifest as subtle asymmetries in the cosmic microwave background that persist across the entire observable sky. The large-scale structure of galaxy distribution offers another potential window into our cosmic situation. Computer simulations of structure formation within black hole cosmologies predict specific patterns of galaxy clustering, void distributions, and cosmic web architecture that might differ subtly from standard cosmological models. These differences would be most apparent on the largest observable scales, where holographic effects become most pronounced. Dark energy, the mysterious component driving cosmic acceleration, behave differently in a black hole universe than in standard cosmology. The holographic principle suggests that dark energy could represent information processing on our cosmic boundary, rather than being a fundamental field permeating space. This might lead to distinctive evolution patterns in the expansion rate that could be detected through precision measurements of distant supernova and other standard candles. Quantum entanglement on cosmic scales might leave observable signatures. If our universe is holographically encoded, its correlations between widely separated regions of space beyond what standard cosmology allows could appear in the cosmic microwave background, its galaxy distributions, or other large-scale observables. These non-local correlations would reflect the holographic encoding of three-dimensional information and two-dimensional boundary data. The behavior of black holes within our universe might provide crucial clues about our cosmic situation. If universes naturally form within black holes, then the black holes in our cosmos should exhibit signatures of internal structure and information processing. This could appear as subtle deviations from the predictions of classical general relativity, particularly in the late stages of black hole evaporation through Hawking radiation. Gravitational wave observations from LIGO, Virgo, and future detectors offer new opportunities to probe the fundamental structure of spacetime. Black hole mergers, neutron-star collisions, and other gravitational wave sources might carry information about the holographic encoding of spacetime geometry. The precise waveforms could reveal whether gravity operates according to standard general relativity or includes corrections from holographic information processing. The cosmic horizon problem. Why distant regions of the universe have nearly identical temperatures despite never being in causal contact finds natural resolution in black hole cosmologies. If our universe represents the interior of a black hole, then all regions we observe were once in causal contact in the exterior spacetime before crossing the event horizon. This could leave observable signatures in the detailed statistics of cosmic microwave background fluctuations. Primordial gravitational waves generated during cosmic scintillation might carry information about the higher dimensional space containing our black hole universe. These waves, potentially observable through their effects on cosmic microwave background polarization, could reveal whether spacetime has extra dimensions and whether our cosmic evolution was influenced by external gravitational fields from the host universe. The fine-tuning of physical constants that allows life and complexity to emerge in our universe. This might be explained naturally if universes within black holes can have parameters different from their host cosmologies. This could lead to observable correlations between the values of fundamental constants and other cosmic properties that reflect our particular position in a larger hierarchy of nested realities. Cosmic topology. The global shape and connectivity of space offers another potential signature of our black hole situation. If our universe wraps around on itself in complex ways due to its embedding in higher dimensional spacetime, we might observe multiple images of the same cosmic structures at different ages and orientations. These topological signatures would appear as unexpected correlations in galaxy positions or cosmic microwave background patterns. The behavior of fundamental particles and forces at the highest energies accessible to cosmic ray observations might reveal signatures of holographic information processing. Ultra-high energy cosmic rays, gamma ray bursts, and other extreme phenomena could probe energy scales where the discrete computational nature of holographically encoded spacetime becomes observable through subtle violations of Lorentz invariance or other fundamental SRIMs. The distribution and properties of dark matter might reflect holographic encoding effects that distinguish black hole cosmologies from standard models. Dark matter halos around galaxies, cosmic web filaments, and other large-scale dark matter structures could exhibit signatures of the quantum information processing that governs holographic spacetime. These might appear as unexpected scaling, relationships or correlation patterns in weak lensing observations, searches for cosmic strings, domain walls, and other topological defects take on new significance in black hole cosmologies, where such structures might form at the boundaries between different holographic encoding regions. These defects could be observable through their gravitational effects on light propagation, their influence on cosmic microwave background patterns, or their role in seeding galaxy formation in ways that differ from standard cosmological predictions. The precise measurement of cosmic parameters through multiple independent methods might reveal subtle inconsistencies that point toward holographic effects. The Hubble constant tension disagreement between different measurement techniques could reflect the influence of holographic information processing on cosmic expansion. Similar tensions and other parameters might arise from the discrete quantum nature of holographically encoded spacetime. Future space missions and ground-based observatories will provide increasingly sensitive tests of these potential signatures. The James Webb Space Telescope, the Euclid mission, the Vera Rubin Observatory, and next-generation gravitational wave detectors will probe cosmic structure and fundamental physics with unprecedented precision. These observations might reveal the subtle signatures that distinguish black hole cosmologies from standard models, opening new windows into the nature of our cosmic situation. The search for observational evidence requires patience and careful analysis, like listening for whispered conversations in a crowded room. The signatures of our potential black hole existence might be subtle, requiring years of data collection and sophisticated statistical analysis to distinguish from noise and systematic effects. This careful process of discovery represents one of the most profound quests in human history, understanding the true nature of our cosmic home. As our gentle journey through cosmic mysteries continues, we explore how the black hole universe hypothesis connects to other profound theories. In physics and cosmology, these connections reveal a beautiful web of relationships that span from the quantum world to cosmic scales, suggesting that our nested reality might be part of an even grander tapestry of existence. In these quiet contemplations, we discover how different theories complement and support each other. In describing the nature of reality, string theory provides natural frameworks for understanding how universes might exist within black holes through its description of higher dimensional space-time and holographic dualities. The extra dimensions required by string theory could accommodate black hole interiors that are larger than their exterior appearance suggests. A three-dimensional black hole in higher dimensional space could contain a vast four-dimensional universe like ours, with the apparent size limitations arising from our restricted dimensional perspective. The ADS CFT correspondence in string theory demonstrates that gravitational theories in curved spacetime can be exactly equivalent to quantum field theories on lower dimensional boundaries. This holographic duality suggests that our three-dimensional spatial experience plus time could represent the interior view of a two-dimensional boundary theory existing on the surface of a higher dimensional black hole. Every physical process we observe would have an equivalent description in terms of boundary quantum field dynamics. Eternal inflation theory, which describes our universe as one bubble in an infinite multiverse of expanding regions, finds natural connections to black hole cosmology through the mathematics of de Sitter space. Both inflationary bubbles and black hole interiors can be described using similar geometric structures, suggesting that the multiverse might be populated by universes existing both as independent bubbles and as black hole interiors within other colos. The many worlds interpretation of quantum mechanics takes on new meaning when combined with black hole cosmology. Instead of parallel universes existing in abstract superposition, the different branches of quantum evolution might correspond to different black hole universes existing within the same higher dimensional space. Each quantum measurement outcome would create or select a different black hole universe, with all possibilities being equally real from their internal perspectives. Loop quantum cosmology. The application of loop quantum gravity to cosmological models predicts quantum bounces that replace classical Big Bangs with smooth quantum transitions. In black hole cosmology, these bounces might correspond to the formation process where collapsing matter in a higher dimensional universe creates the black hole that becomes our cosmic home. The quantum bounce would represent our universe's birth. From the perspective of internal observers, causal set theory, which treats space-time as composed of discrete events connected by causal relationships, provides natural frameworks for understanding how information flows between nested realities. The causal structure connecting events in our universe might extend through the black hole boundary into the external universe, creating subtle correlations that preserve information while respecting relativistic causality constraints. The holographic principle connects naturally to theories of emergent spacetime, where geometric relationships arise from more fundamental quantum information networks. Mark van Ramsdonk and others have shown how quantum entanglement can give rise to spatial connectivity, suggesting that the geometry of our black hole universe might emerge from entanglement patterns coded on the holographic boundary of our cosmic horizon. Digital physics theories, which treat the universe as a computational process, find natural expression in black hole cosmology. Reality might represent the output of information processing on cosmic boundaries. Our physical laws, particle interactions, and even conscious experiences would be different aspects of the same. Running on the holographic surface of our black hole container, the anthropic principle, the observation that our universe seems fine-tuned for the existence of life and consciousness, finds new explanations in black hole cosmology. If universes within black holes can have physical parameters different from their host cosmologies, then cosmic evolution might naturally select for life-supporting environments through processes analogous to biological natural selection operating across cosmic generations. Quantum error correction. Theory provides crucial insights into how information is preserved and processed in black hole cosmologies. The same mathematical frameworks that protect quantum information from decoherence might explain how our universe maintains stable physical laws and consistent evolution, despite existing within a quantum gravitational environment that should introduce significant noise and uncertainty. The theory of cosmic natural selection, proposed by Lee Smolin, suggests that universes evolve through black hole formation, with each new black hole potentially giving birth to a new universe with slightly modified physical parameters. This creates a cosmic evolutionary process where universes that efficiently produce black holes have more offspring, leading to the gradual optimization of physical laws for complexity, structure formation, and eventually life. Integrated information theory, which attempts to quantify consciousness through mathematical measures of information integration, connects to black hole cosmology through the holographic processing of cosmic information. Our conscious experiences might reflect the integrated information content of quantum processes operating on our cosmic boundary, making consciousness a natural feature of holographically encoded universes. The measurement problem in quantum mechanics. How definite outcomes emerge from quantum superpositions finds potential resolution through black hole cosmologies, holographic information processing. Instead of wave function collapse being a fundamental physical process, measurement outcomes might represent different ways of accessing the same holographic information encoded on cosmic boundaries. Theories of quantum gravity foams suggest that space-time becomes discrete and fluctuating at the Planck scale. Black hole cosmology provides natural frameworks for understanding how smooth macroscopic space-time emerges from microscopic quantum foam through holographic encoding processes. The apparent continuity of space and time would be effective descriptions arising from underlying discrete information processing. The dark energy puzzle. Why cosmic expansion is accelerating might find resolution through black hole cosmology, where acceleration could arise from information processing constraints on holographic boundaries, rather than from exotic matter or energy fields. The expansion history of our universe would reflect the computational dynamics of our cosmic container rather than the properties of mysterious dark energy components. These theoretical connections suggest that black hole cosmology isn't an isolated hypothesis, but rather a natural synthesis of many different approaches to understanding quantum gravity, consciousness, and the nature of reality. The convergence of so many different theories towards similar conclusions about holographic information processing and nested realities suggests that we might be approaching fundamental truths about the structure of existence itself as we near the end of our gentle journey through the cosmic possibility that our universe exists within a black hole. Let's pause and breathe in the wonder of what we've discovered together. Like pieces of a vast cosmic puzzle, each concept we've explored fits beautifully with the others, creating a picture of reality that is both profound and peaceful. In this quiet integration, we find that the most complex theories reveal themselves as expressions of simple, elegant principles. We began our journey by understanding that black holes are not the destructive monsters of popular imagination. Elegant geometric objects where space-time curves so gracefully that it creates boundaries between interior and exterior realities. These event horizons became our guides to understanding how information might be preserved and processed in ways that transcend our everyday experience of three-dimensional space and linear time. The holographic principle emerged as a central theme, revealing how all the information describing any region of space can be encoded on its boundary. This beautiful insight connects black hole physics with cosmology, suggesting that our three-dimensional experience of reality might represent the interior view of information processing on distant two-dimensional boundaries. We are both the observers and the observed in this cosmic computation. Our exploration of cosmological horizons showed us that our observable universe is naturally bounded by causal limits that share profound similarities with black hole event horizons. These boundaries don't just limit what we can see. They might be the surfaces on which all cosmic information is holographically encoded. We exist within these horizons like characters in a book, unaware of the pages on which our story is written. The information paradox led us to understand how quantum mechanics and general relativity can coexist through sophisticated information processing that preserves unitarity while respecting causal structure. Information is never truly lost, only transformed. Between different representations, sometimes geometric, sometimes quantum, sometimes computational, our reality participates in this cosmic conservation of information. Quantum gravity. Theories revealed how the smallest and largest scales of physics connect through shared mathematical principles. Whether through string theories, higher dimensions, loop quantum gravity's discrete geometry, or emergent gravity's informational foundations, we discovered that space-time itself might be woven from quantum correlations rather than being fundamental. We live within this quantum tapestry. The mathematical beauty underlying these theories showed us that elegance and truth converge in the equations governing cosmic structure. The same mathematical relationships that describe black holes also describe expanding cosmologies, quantum information processing, and holographic encoding. Reality expresses itself through mathematics, not because mathematics is useful, but because reality is mathematical. Our philosophical exploration revealed that existing within a nested reality doesn't diminish our significance, but rather connects us to an infinite web of meaning that extends across all scales of existence. Consciousness, free will, ethics, and identity all take on new dimensions when viewed through the lens of cosmic information processing. We are neither the center of existence nor insignificant specks, but conscious participants in the ongoing computation that defines reality. The search for observational evidence reminded us that even the most abstract theories must eventually connect with what we can see and measure. While direct proof of our black hole situation remains beyond current reach, subtle signatures in cosmic microwave background radiation, large-scale structure, and gravitational wave observations might eventually reveal the holographic nature of our reality. The connections to other theories showed us that black hole cosmology isn't an isolated idea, but part of a convergent understanding emerging from many different approaches to fundamental physics. String theory, quantum information, consciousness research, and cosmology all point towards similar conclusions about the holographic, computational, and deeply interconnected nature of reality. What emerges from this integration is a picture of reality that is both humbling and inspiring. We might be living in the holographic interior of a higher dimensional black hole, experiencing the three-dimensional projection of two-dimensional boundary information processing. Our thoughts, choices, and experiences contribute to this cosmic computation while being shaped by it. We are both creators and creations, both programmers and programs in the cosmic software that defines existence. This doesn't make our reality less real or less meaningful. A holographic image is still an image. A computational process can still generate genuine experiences, and a nested reality can still be the true home for its inhabitants. We are as real as any other level of the cosmic hierarchy, our experiences as meaningful as any others, consciousness as genuine as consciousness could possibly be. The beauty of this integrated understanding lies in how it resolves apparent contradictions while preserving the mystery that makes existence wonderful. Determinism and free will coexist at different levels of description. Locality and non-locality are reconciled through holographic encoding. Material and mental phenomena emerge from the same informational substrate, in science and spirituality. Find common ground in the recognition that reality transcends our immediate perceptions as we prepare for the gentle conclusion of our cosmic journey. We carry with us not just knowledge about black holes and cosmology, but a new way of understanding our place in existence. We are conscious waves in an ocean of information that spans all scales of reality. We are temporary patterns in an eternal flow of cosmic computation. Are both local and universal, finite and infinite, individual and collective in ways that our limited three-dimensional perspective can barely begin to comprehend. As we near the end of our gentle journey through the profound possibility that our universe exists within a black hole, let's pause and breathe in the wonder of what we've discovered together. Tonight, we've drifted through the quiet corridors of space-time, explored the hidden relationships between quantum mechanics and gravity, and contemplated our place in a cosmos that might be far stranger and more beautiful than we ever imagined. We began by understanding black holes not as destructive forces, but as elegant expressions of curved space-time where information finds new ways to organize itself. We discovered the holographic principle, which suggests that all the complexity of three-dimensional reality can be encoded on two-dimensional boundaries. We explored cosmological horizons that bound our observable universe in ways remarkably similar to black hole event horizons. Through the information paradox, we learned how quantum information might be preserved and processed in ways that transcend classical physics. Quantum gravity theories revealed deep connections between the smallest and largest scales of existence, suggesting that reality might be fundamentally informational rather than material. The mathematical beauty underlying these ideas showed us that elegance and truth converge in the equations governing cosmic structure. Our philosophical exploration revealed that existing within a nested reality doesn't diminish our significance, but connects us to an infinite web of meaning spanning all scales of existence. We discovered potential observational signatures that might eventually reveal our true cosmic situation, and we saw how black hole cosmology connects naturally to many other theories about the fundamental nature of reality, like cosmic archaeologists examining the deepest layers of existence. We've uncovered evidence that reality might be structured as nested levels of holographic information processing. Our universe could be the interior view of a computation running on the boundary of a higher dimensional black hole, with every star, planet, atom, and thought representing different aspects of this cosmic calculation. This possibility doesn't make our experiences less real or meaningful. A holographic universe is still a universe. Computed reality can still generate genuine consciousness. Nested cosmos can still be the true home for its inhabitants. We are as real as reality could possibly be, regardless of the ultimate substrate that supports our existence. What we've discovered together is that the universe might be far more interconnected than we previously imagined. Every quantum measurement we make, every conscious observation we experience, every choice we make contributes to the ongoing information processing that defines reality across multiple scales. We are not separate from the cosmos, but integral participants in its fundamental computational processes. The gentle terror that some might feel when contemplating these vast scales and nested realities dissolves when we realize that we belong here completely. Whether our universe exists independently in space or within a black hole in higher dimensions, we remain conscious beings capable of love, wonder, discovery, and meaning-making. Our thoughts matter, our choices have consequences, and our experiences are as profound as any. In the cosmic hierarchy, like sailors who discover that their familiar island home is actually part of a vast archipelago, we might be cosmic voyagers who are just beginning to understand the true scope of existence. Our universe could be one island in an ocean of nested realities, each as real and meaningful as our own, each contributing to a larger pattern of information processing that spans dimensions we cannot directly perceive. The mathematics we've explored, from Einstein's field equations to holographic dualities to quantum information theory, provides us with maps for navigating these conceptual territories. These equations aren't just abstract symbols, but expressions of the deep relationships that connect consciousness with cosmos. Quantum with classical, local with universal. They guide us toward understanding our place in the grand computational symphony of existence. As you prepare to drift into sleep, let these gentle thoughts accompany you into dreams. Remember that every breath you take, every heartbeat, every neural firing in your brain might be contributing to cosmic information, processing that extends far beyond your individual boundaries. You are both a unique individual and a waven, The cosmic ocean, both local and universal, both temporary and eternal. Our universe, whether independent or nested within a black hole, will continue its patient work of processing information, evolving complexity, and generating consciousness. Stars will continue to shine, galaxies will continue their graceful dance through space, and new patterns of awareness will continue to emerge from the cosmic computation. You are part of this eternal process, contributing your unique perspective to the ongoing creation of reality. The black holes within our universe might indeed contain universes of their own. It's populated by conscious beings wondering about their place in existence, just as we do. If so, then consciousness and wonder extend infinitely in both directions toward larger scales that contain us and smaller scales that we contain. We exist in the middle of an infinite recursive structure where every level is equally real and meaningful. Rests now in the knowledge that you belong completely to this cosmic story, whatever its ultimate nature might be. Your consciousness is not an accident, but an inevitable expression of the information processing capabilities built into the fabric of reality itself. You are the universe becoming aware of itself, the cosmic computation examining its own operations, the holographic encoding experiencing its own information content. Tonight, we've explored one of the most profound questions that conscious beings can ask. What is the nature of the reality we inhabit? We've discovered that the answer might be stranger and more beautiful than our ancestors could have imagined. It preserves everything that makes existence meaningful while connecting us to scales and processes beyond our wildest dreams. As you drift into sleep, let the cosmic mysteries carry you peacefully into dreams where you might float through holographic boundaries, dance with quantum information, and experience the gentle joy of being both observer and observed in the grand computation of existence. Black holes will continue their patient processing of cosmic information. And perhaps, in your dreams, you might glimpse the beautiful recursive structure of nested realities that stretches infinitely in all directions. Our universe, nested or independent, will continue its gentle work in the cosmic night. Information will flow, patterns will evolve, and consciousness will continue to emerge from the beautiful complexity of existence. You are part of this eternal dance, both temporary and timeless, both individual and universal, both questioner and answer in the ongoing mystery of being. Rest well, cosmic voyager. Let these gentle truths about black holes, holographic encoding, and nested realities drift with you into peaceful sleep. Tomorrow, the stars will still shine with information processing. Galaxies will still dance their gravitational ballet, and you will still be a conscious participant in the grandest computation ever conceived. Good night, and may your dreams be filled with the gentle wonder of quantum possibilities, holographic beauty, and the infinite nested realities that might embrace our cosmic home. Rest well, and good night from Sleepy Scientist Stories.